Why do powder bed fusion parts fail in additive manufacturing? Imagine building a complex metal part layer by layer, only to find it cracks or has tiny holes when finished. That's what can happen in powder bed fusion, a popular method in additive manufacturing. This process uses a laser or electron beam to melt powdered material into solid parts. But sometimes, these parts don't turn out as planned. Why is that? Let's explore the main reasons behind failures in powder bed fusion parts. The most common issue is porosity, which means tiny holes or gaps inside the part. Porosity happens when gas gets trapped during solidification or when powder particles don't fully melt. There are different types of porosity. Lack of fusion porosity occurs when the laser doesn't deliver enough energy, leaving unmelted powder between layers. This creates weak spots that can crack under stress. Keyhole porosity is caused by too much laser energy creating vapor cavities that trap gas bubbles. Gas entrapment porosity results from turbulence in the melt pool, trapping gases as the material cools. These tiny holes act like stress concentrators, making the part more likely to break during use. Lack of fusion is a specific problem where layers don't bond properly. It happens if the laser power is too low or the scanning speed is too fast. Poor heat dissipation can also cause incomplete melting. Sometimes, oxide layers on powder particles prevent proper bonding, creating weak points. These weak spots reduce the part's strength and make cracks more likely to form. Another issue is balling, where the molten metal forms spheres instead of smooth tracks. This occurs if the melt pool becomes unstable, leading to uneven surfaces and poor layer bonding. It weakens the overall structure. Cracking can also happen because of thermal stresses. When the part heats up and cools down quickly, it can develop cracks, especially in materials sensitive to temperature changes. Contamination is another factor. Oxide layers or impurities on powder particles can become trapped in the melt, creating inclusions that serve as crack initiation sites. Process parameters play a big role too. If laser power, scan speed, or hatch spacing are not set correctly, defects increase. Using low-quality powder or improper shielding gases can also lead to defects. For example, inadequate shielding can allow oxygen or moisture to contaminate the powder, causing oxidation and inclusions. All these defects weaken the part's mechanical properties. They serve as starting points for fatigue cracks, especially under cyclic loads. To prevent failures, manufacturers optimize process settings to ensure complete melting and strong bonding. Controlling the thermal environment reduces residual stresses. Using high-quality powders and post-processing techniques like hot isostatic pressing can close internal pores and improve strength. Understanding these failure causes helps in developing better monitoring and control during manufacturing. This way, parts become more reliable, last longer, and perform better in real-world applications. Addressing these issues is key to making additive manufacturing a dependable solution for producing complex, high-performance parts.